Okay, let's do this quiz 5.2. Alright, so this is on substitution, integration by substitution. Later on, it gets mixed together. Like I said, you'll encounter integration problems where you don't know how you're going to approach it. Maybe it's a basic one where you just do the power rule. Maybe you have to use substitution. Maybe you have to do any one of the many more techniques you're going to learn in the future. But this one is definitely all substitution. And I'm going to kind of fly through a little bit quicker than I did in the notes. Because the main thing, you presumably got some practice. And I got a lot of problems apparently. And yeah, so we're just going to grind it out. The main thing is you pick your u correctly so that all the pieces fit. Number 1. I have an ln squared x over x dx. And we did one similar where if you have an ln or any power of ln, if you do u as equal to ln, your du will equal, well, so I'm mentally going through what I could set u to. There's not that many pieces here, but definitely if I set u to be ln of x, my du has that 1 over x dx, which accounts for that bottom. So this will work out perfectly. Alright, so when I rewrite it, it's going to be ln squared right there times du, since the du covers the 1 over x dx. Alright, that's it. Moving on, it's going to be, I'm going to take the antiderivative now. It's going to be 1/3 u cubed via the power rule plus c. And my last step is to put it back together using u is equal to ln of x. It's going to be ln x cubed. And so that's your answer right there. U is equal to ln of x, and that x in the bottom gets accounted for by the du. Number 2. I got x e to the, and I have an expression in the exponent, 6 minus 2x squared. Okay, you can't really do anything other than to have an e to a single power, so I'll probably set u to be that. Kind of anticipating what's going to happen when I do my d. If that's u, my d is going to have x to the 1 power. That's going to account for that x. A lot of constants I'll have to manage, but apart from that, it'll definitely work. So u will be that exponent there. My du is going to be, that becomes 0. I'm going to get negative 4x dx. I'll move that negative 4 over and get a clean x dx, which means I'm going to have x dx is equal to negative 1/4 du, and I'm ready to go. I'm ready to put it together. The e to the whatever piece is going to be e to the, that exponent is going to be u now. What's left is that x with the dx together, I'm treating as, because together they equal negative 1/4 du. And it worked, all the pieces fit. I'm going to pull that negative 1/4 out. And I end up with just an antiderivative of e to the u du, which is just e to the u plus c. And so my final answer will be negative 1/4 e to the u. Instead of u, I want the expression that I set u to be. 6 minus 2x squared plus c. Next one, I didn't do one like this in the notes, but it just has, it's not as bad as it looks. I have x squared, e to the x squared, minus ln of 3x, all over x dx. Oh, all over 2x dx. Okay. Alright, a lot going on in this problem, but notice your denominators, you have 2 terms on top, and your denominator is a single term, a single monomial, power of x. So we've done it with polynomials, but the same thing applies here. I can split it up, put each of those terms on top over its own denominator. So now it's just 2 separate terms for one integral. I'm also going to, because this is the first time I'm going to be doing it, I'm going to reduce this. It's going to be x e to the x squared, over 2. Yeah. And I'm going to cap that off, and I'm going to split up the other one. So I'm going to split it into 2 separate integrals, because Each one will require a separate technique. Both of them are going to involve substitution. This is similar to number 2 on the quiz that we just did. This is going to be similar to number 1 on the quiz that we just did. The different constants and slightly different things, but the same substitutions will work there and there, but they're different substitutions. I'm going to clean it up a little bit. I'll pull out these constants here. You don't have to, but I like to pull out as much constants as I can. And now I have that, which means I'm going to be able to get through that with a u. Let me anticipate what I'm going to be doing. Similar to that one, u is equal to x squared, my exponent. My d is going to cover that x dx. It'll have a constant coming out. Again, the constants, you just got to, keep track of them, but they're not going to affect whether the pieces will fit or not. They're all just movable. My du is going to be 2x dx. So that's going to work for this integral, but I'm going to need a separate, different substitution there because it's a different technique. So I'm going to pull out the half as well. I can't pull out that x, so it's going to be on the bottom. I could use a rule for logarithms to split that up, but I don't have to. I'm not going to do it. Similar to number 1, I'm going to let u be the logarithm. In this case, there's no power, but it's still going to be helpful to make u equal to ln of x, because then my du is going to equal. And a little bit trickier this time, it's not like exactly like number 1. I have to do the chain rule on this. It's going to be 1 over the inside times the derivative of the inside function. 3x is 3 dx. And when I clean that up, I'm going to get 1 over x dx. Okay, so that substitution will work on this. This substitution will work on that. And I'm going to just do them separately. They're different u's. So here's one situation where sometimes I switch it to w. Or you can work with 2 u's. Just make sure you know that when you get the antiderivative of this in terms of u, you got to substitute back x squared for that u. And when you do an antiderivative with respect to u here, you've got to substitute back in ln of 3x for that u. They're 2 different u's. Maybe be better to, you can do them separately on scratch paper and then put your final answer together. Anyway, the main thing here is organize it. Be careful. I'm going to use w. I'm going to choose to work on both at the same time, but use a different variable for that second substitution. Okay, I'm going to do a lot of space for this. It's not bad, but it's a lot going on. Oh, sorry, let me backtrack. So I'm going to be using a w there. And let me do it cleanly. I was sort of half-assing that. Okay, looking at this, my u is going to be equal to x squared. My d will equal 2x dx. I'll move that half over. Okay, so very similar to things I've done already. And so now I'm going to rewrite the integral. 1/2 integral. The e to the x squared becomes e to the u. And then my x dx becomes a 1/2 du. I'm going to continue that over here. So I'm going to ultimately get 1/4 e to the u du. I can finish that entire problem up and get that first piece of my final answer if I want. Do I want to do that? Yeah, let me just finish it up. Okay, so I pulled that second half out and it became 1/4. I'm going to do the antiderivative. The plus c I'm going to put at the end, so I'll hold off on it for now. My antiderivative is e to the u, drop the integral sign, and substitute back in u. In this case it was x squared. Okay, that's my antiderivative of that first integral, plus c. If that was the only thing I'm doing. It's not the only thing I'm doing. I'm also doing this one. So this one I'm going to use another variable substitution, but I'll use w. It's going to be the ln, because when I do that derivative of that, my dw will have an x in the bottom, 1 over x. dw is equal to, as I said before, chain rule, 1 over times the 3 derivative inside dx. The 3's cancel, and I get dw is equal to 1 over x dx. And what I'm going to do is rewrite this as minus 1/2 integral. My w is right there. The 1 over x dx becomes dw, and that's my integral rewritten in terms of w, and that's going to be a power rule. This is w to the 1. I'm going to bump it up to 2, divide by that 2. So I'll do it right over here. Let me rewrite it first. Okay, so I'm going to do the power rule on that. That's going to be w to the 1 plus 1 is 2. I'm going to divide by that 2. And here's where I'm going to tack on the plus c for the whole thing. Alright, and I got to substitute back in place of w, so it's going to be 1/4, 1/2 times 1/2, and then w squared. W was, where was it? Right there. Ln squared of 3x plus c. Okay, and that's your antiderivative of that. Just treating them separately, they require 2 separate substitutions, but because it was a plus or a minus between them, you can literally just do the 2 separate integrals via 2 separate techniques. Next, number 4. Alright, number 4, integral x plus 1, 2x minus 4. Alright. U is x plus 1, my du equals to dx. That accounts for the top, it does not account for the bottom. Usually I want to get the bottom to one thing, so let me try setting u to the bottom. Then my du is going to be equal to 2 dx. That means my bottom is accounted for as a u, my dx is going to convert to a du with a constant floating around. I don't have my top accounted for, so that'll be missing. This is that situation where you can actually account for that extra x on top, doing the substitution and solving it for x. So it's going to be u plus 4 over 2. Add 4 to both sides, divide by 2. Oops, sorry, that's x equals. That gives me x is equal to u plus 4 over 2. So now I can use that to account for all the pieces. So let me make sure we go through this a little more slowly. Oops, also, I forgot to get a clean dx. Move my constant over, like I usually do. Okay. Let me rewrite the integral here. And go through the pieces one by one. Alright, I set my u to be the denominator, 2x minus 4, so that becomes a u. My dx is equal to 1/2 du, so that converts cleanly, somewhat cleanly, to a du, which is just a constant. The issue is now I have an x plus 1 that is not usually not accounted for, and you get stuck, and I don't know how I'm going to do it. But again, this u being a linear expression in x means you can solve for x, and you get a linear expression in u, and actually use that. X is equal to u plus 4 over 2. Do I want to actually? Yeah, I'm just gonna cram. So I'm gonna cram it up here. I'll have to clean it up a little bit, but so oh shit. Let me put it back. Okay, the x is u plus 4 over 2. So let me just replace that. Okay, and there we go. My dx became half du. My denominator became a clean u, and I had to solve for x and replace that x on top with a u plus 4 over 2, and it's still got a plus 1 there that I'll have to like simplify a little bit. Oh, how am I going to do this? Let me think. There's different ways to manipulate it. I'm going to treat this as, I could have fixed that a little bit, but I'm going to multiply top and bottom by 2 to clear out those little denominators. That was one technique for cleaning up a fraction within a fraction. It's going to give me u plus 4 plus 2, because that 2 multiplies by everything, over 2u. I still got that 1/2 there. And so I'm just cleaning it up and getting into a much simpler form than this, because it will clean up a little bit. Let me see. I'll get u plus 6 there. I'll have 2u and another half, which means that I can pull out a 4. That 2 and that 2 can come out as a constant, leaving with just a u there. In my top, I can't really do anything more with leaving this u plus 6 du. Okay, so this substitution of u being in the denominator did work out. I did have to account for the extra x in the numerator by solving for x. It didn't work out to integral that it is simpler than the original, because this one has a single factor on the bottom, and I can now split it up. Putting each term on top over its own denominator, it's going to be u over u plus 6 over u. Still cleaning up. Still have not taken an antiderivative. And a lot of times you lose track of constants, so be careful to bring everything down as you go. I'm going to have a 1 plus a 6 over u. And I'm ready to go. Power rule, except for that one. That one is not a power rule. Think about that while I work on it. Okay. I'm going to put a big brackets because that 1/4 will apply to both the antiderivatives I get for both terms, and it's easy to forget if you don't put the whole thing in brackets or parentheses. Antiderivative of 1 is just u. Antiderivative of 6u to the negative 1 is not a power rule situation. It is a log situation. It's 1 over u right there. And the 6 is just a constant that comes down. So 6 ln of u plus c. Plug back in my u, 2x minus 4. Replace that u with 2x minus 4. Replace that u with 2x minus 4 plus c. I'm going to distribute, that's going to be 1/2 x minus 1 plus 6 ln of 2x minus 4 plus c. That's good, although they do like you to note that this is a constant and you can absorb it into the c. So combine it with the arbitrary constants. All the other terms have to be left though. You need a 1/2 x plus a 6 ln of 2x minus 4. You could factor that, but now you don't have to. And then that minus 1 and that c combining for a new arbitrary constant c, but it's arbitrary anyway. So that's it. Okay, so that one had that issue of an extra x on top, and then having to solve for x and do an extra step in the substitution. An extra piece had to be put together. Number 5. 4x plus 2 over the cube root of 2x cubed plus 3x plus 4. And any kind of radical, you can't apply it to the individual terms. You're not going to be able to break it up in that way. You cannot simplify it. So we'll have to just work with this. No more simplification, not really anything to manipulate that will work. You can factor out a 2 on top, but that's it, and it's not really going to be too helpful. It may be helpful. I basically, the best bet is to set u to be that whole radicand in the denominator. Then it'll be a u and a negative 1/3 power for that cube root, and that'll be a power rule situation. The top is unaccounted for, but maybe, if you'll notice, copy. Okay, I actually wrote it wrong. Well, I'm going to be honest with you, I didn't write it wrong. I had it set up so it wouldn't work out. So I had to fix it on the quiz. Okay, so while I fix it and before I post it, it'll be fixed. So you're seeing this on your paper, 4x squared plus 2. If I didn't have that square, it's not going to work out. Again, these are in design where the pieces just, well, not coincidentally, these pieces fit very nicely. They're designed to fit very nicely. And so I'm going to be setting u, as I talked about, to my denominator, because then it'll be u to the negative 1/3 power. I'm hoping that when I do my du, that accounts for the other piece which is on top, which is why I need that to be designed perfectly to be a multiple of what I get here. 6x squared plus 3 dx. So That's what I get when I do my derivative of du. It is not the same at the top. It's not exactly accounted for. But one thing to note is that it does have an x squared and a constant. That's why I needed that x squared, by the way. X squared and a constant, and I've got to manipulate it so it'll work. It will work. It's designed to work. I could factor out a 3 here, and I'll get x squared plus 1 dx. And I can note that that's just a multiple of x squared plus 1, so maybe I should rewrite my integral. Maybe I should have factored that 2 to begin with. I didn't know that ahead of time, but now it's looking like, yeah, I definitely want to factor that 2, and oops, I forgot this 2 over here. Alright, I have no excuse. It's actually afternoon at this point. Okay, factoring out that 2 on top so that I can see that they do have a common factor. My numerator and my du is equal to whatever dx does have that common factor of 2x squared plus 1. Let me manipulate this a little bit more. I'm going to divide by that 3. But I will leave that clean 2x squared plus 1 dx. And I'm ready to go. It'll work. So the idea now, it did work out perfectly where that factor with the dx does appear here after I factor out the 3, so it's equal to 1/3 du. That 2 was separate. I had to factor that out to make it work, so that's factored there. And my whole denominator is just the cube root of u. So that's how it worked out. It looked really ugly. It did take a little manipulation to get it to work, but the pieces did fit. I'm ready to actually start doing this now. I'm going to pull out the 2/3. I'm going to rewrite that as u to the negative 1/3 power du, and that's what I have to do. This is a power rule situation. We've had it with fractions. It's the same thing. 2/3. I'm going to add 1 to that, which will be 2/3 power. I have to divide by that power plus the c. When I flip it, it becomes 3/2. Flip it, becomes 3/2 times that 2/3 will cancel, and so I have no coefficient. It'll be a 1. So this will ultimately simplify to u to the 2/3 plus c. Final answer is me going back to x, and my u is equal to all of that, so it's going to be 2x cubed plus 3x plus 4 to the 2/3 power plus c, and that's my answer there. Okay, next one is a little bit tricky. Oof, it's really tricky. It comes up in the homework in a later section, so I want to make sure. Oh, you guys know what number that was, right? I forgot to write it. That was number 5. Okay, and then we're doing number 6 now. I have e to the x plus e to the negative x over e to the x minus e to the negative x. All right. If I set u to be the top, my du via the chain rule, derivative of e to the x is e to the x. Derivative of e to the negative x is chain rule on it with, it's going to be e, the inside function left alone, times the derivative of that negative x. So it's ultimately going to be e x minus e to the negative x. Now, that accounts for the bottom, but that's not where it is here. So this is not working out specifically. There is a subtle difference between the plus and minus there. So this is not the correct way, but let me just make sure we don't confuse it and think it is working. I do see a lot of the correct pieces. They are not in the correct place though. the way I did it was, and I knew I was going to be wrong, but anyway, I just want to make sure. I said u to be the top with a plus in the middle. So as of now, I'll have u on top. My dx is there, which means that I have, but this piece is on the bottom. And so I don't exactly have that. So it's not working out. This together with this, let me rewrite it. Splitting it up, I have my numerator. And then this e to the x minus e to the negative x is on the bottom. And so that's what I have. And I don't get that exactly when I do my du. So that is not the same thing as a du, because that factor that I do see it over there, but it's on the bottom on this one. And it's not on the bottom here. And you can't get du on, you can't put du on the bottom of your integral. It's got to be on the ground level. So this is not working out. But you can kind of see how the derivatives are, you know, related at the top and bottom. So what I want to do, after I rewrite this and clean it up, I want to set, let me just backtrack. I want to set u to be the bottom. It was probably a good idea anyway from the beginning, so that you oftentimes, if you have an expression, a complicated expression in your denominator, oftentimes you're going to at least try to set u to be that and see if the du accounts for the top or whatever is left. If I set u to be my denominator with a minus there, and I do my derivative, it's going to be, I'll work it out slowly, minus, I'm going to chain rule on that, it's going to be e to the negative x times -1 from the chain rule. That negative is going to cancel. And I will get e to the x plus e to the negative x dx. And that is equivalent to that together with that. So that is my du right there. So it does work out. This is the way to go, setting u to be my denominator. Alright, so that whole thing is du. My denominator is just u, and that's what I have, du over u. And that, the antiderivative of that is ln of u. Again, it's like 1 over u du. They'll leave it like that, but make sure you interpret that as your integrand is 1 over u. Alright, final step, rewrite it as ln of e to the x minus e to the negative x. There's some manipulation that you could do to get those e's to cancel, but you cannot split up a logarithm. There is no rule where it splits up a difference, subtraction in there or plus. The rules for logarithms, to recap, are you can split up a product, or you can split up a quotient into the sum or difference of logarithms. That's a thing that's useful in some situations. A product splits up into a sum of 2 separate logarithms. Quotient splits up into a difference of 2 separate logarithms. Log of a sum doesn't break down. You can't split that up. There's no rule for that. And same thing if it's a difference. So this is not something you can apply that logarithm to each one separately. It'd be nice because then they would cancel a lot, but you cannot. There is no rule for that. Okay, and that's it. Plus c, I forgot. I need -1 for that. Alright, so that was a little bit of trial and error now. Like I said, a lot of times it is trial and error. Last couple of problems. Okay, I wanted you to get a feel for the fact that 7, 8, and 9, the same thing's going to happen over and over. And it's good, especially when you move into the next level, to not have to literally write out a u and then a du and work it out slowly every time when it's just a coefficient, a multiple of x. So I'll look at the first one, number 7, writing out the actual substitution I'm doing, but then I'm going to try and just talk about how we can just do 8 and 9 using what we just did and knowing what's going to happen with that 4 and where it ends up. Based on, we want to set u to be that 4x, because I can only do e to the u as my antiderivative, so I need to set that whole exponent to be 4x, or to be u. My du will be 4 dx, which means when I isolate dx, I get a 1/4. out of there. What am I writing? I get a 1/4 e. And when I put it together, it's going to be e to the u. My dx converts to 1/4 du. So that 4 ends up being a coefficient of 1 over that 4. I do the antiderivative on the e to the u, bringing that 1/4 down. I replace u with its value or its expression of 4x, and that's it. For the antiderivative of an e to some multiple of x, it's going to have that e to that same multiple of x, but that multiple also comes out as a 1 over the reciprocal of that out here. So that's my answer for number 7. Now, if I had a 5x instead, I would set u to be 5x. I would get a 1/5 coming out front instead. And so I would get 1/5 e to the 5x. So it's have the same exponential, e to the 5x, and that coefficient of that x will come out. If it's a linear function, just a multiple times x, you'll get that 1 over that constant. Okay, so knowing that, it's good if you can recognize those, because they come up a lot. And so let's see if we can just do 8 and 9 in the same way, not working on all the steps and just going bam to the final answer, knowing what's happening to that coefficient. It applies to negative coefficients as well. So for number 8, e to the negative 3x, my antiderivative, no work to be done. It is technically u substitution that I'm doing, but I'm going to just jump to knowing how it works. I'm going to get that same exponential, but then I'll have out here to account for that multiple. It has to cancel when I do the chain rule. I'm going to get negative 3 down there, which I can pull up front. So it's going to be a negative 1/3 e to the negative 3x. Number 9. I got e to the negative x. That is the same thing, except my coefficient there is a negative 1. My antiderivative, I'm going to have e to that negative x. I'm going to have 1 divided by that coefficient, which is a negative 1, plus c. 1 divided by negative 1 is just a negative. So that's my antiderivative. And the last problem is me just making you do a bunch of those for them specifically, hoping that by that time you get to those, you'll recognize a pattern. And I don't want to see all the steps. If you can mentally just know what's going to happen with that, all those coefficients in those exponents, I want you to be able to do shortcuts and skip all the steps. Okay, what I got? I got some numbers out front and some coefficients in the exponent. They're all different exponents, so if I did literally do it manually and working all the substitutions out, I'd have to do 4 separate substitutions, 4 separate u's, one for each of the exponents dealing with those multiples. But knowing how it's going to work, I hopefully don't need to do that. I'm going to bring them to. Antiderivative of that is, we did it, yeah, number 7. Okay, but anyway, I don't need to refer to it. I know it's going to be e to the 4x, and then I'm going to get a 1/4 out. And then it'll just combine to that too. E to the negative 3x, oh, I did include the ones that we did. E to the negative 3x times negative 1/3. I'll make sure that's multiplication there. Oh, I got all of them. Okay, and that's going to be minus e to the negative x. It'll be 1 over negative 1. I can simplify that in my head. And last one, I didn't do that one. That's a new one. So it's going to be e to the negative 2x over negative 1/2. Plus c. And I'm out of room, but anyway, I shouldn't roll it so big. It's going to be 1/2 e to the 4x. That's going to be minus 4 e to the negative 3x minus e to the negative x. And what is that? Minus 3 e to the negative 2x plus c. So it's the same pattern happening over and over when it's just a multiple of x. And that applies to a lot of situations. The other common one where you see that happening a lot is trig functions, which we don't do. But So sometimes the substitution, when you see the pattern and you know how it's going to work and you can anticipate what's going to happen, you don't need to actually do all the steps. Okay, it's good to be careful when it's more complicated than this, but nah, just a coefficient, bring them down. Just know it's going to end up with a 1/4, a negative 1/3, a negative 1/1, and a negative 1/2 combined with those other coefficients. All right, that's all I wanted to do with those last few problems, making sure we know that certain patterns will arise and take advantage of that.